Good day to all. Welcome again to our to an ongoing discussion on digital image processing. So, today we will talk about different color models. The title of discussion is Analysis of Images with Different Color Models. So, my name is John Amos. I'm an assistant professor in the Department of Biomedical Engineering at KPR Institute of Engineering and Technology in Coimbatore. So in today's topic, we will discuss about colors and how colors are represented, um, and understand what color models are, what are the different types of color models, and how do you change from one particular color model to a different model. Colors basically in digital image processing is represented as a combination of three fundamental or primitive colors: red, green, and blue. Even in the olden days, in the old technology that we use for color televisions, the cathode ray tube screens used a combination of an additive combination of these three primitive colors of red, green, and blue. So if you look at the presentation, you can see that a combination of red and green gives you the color yellow, the combination of red and blue gives you the color magenta, and the combination of green and blue gives you the color cyan. Uh, so uh, this the concept of color um, came from a very early experiment by Sir Isaac Newton, where sunlight or a source of light, a white light, was dispersed into its fundamental components. Looking at this particular presentation, you can also see that a combination of red, green, and blue, an additive combination of these three primitive colors, will give you white light. So in this you can see the other models as well, and how different shades of colors are obtained by different combinations of these primitive colors. So let's look at certain color models. So the red, green, and blue model, or the RGB model, is represented on a Cartesian axis. So on the horizontal axis, we have green. On the vertical axis, we have blue, and on the depth axis, we have R. So this is a Cartesian axis that we represent, and if you look at the origin gives you the color black, and the extreme, where blue takes a value 1, green takes a value 1, and red takes a value 1. An equal composition of these three colors will give you the color white, and any shade in between black and white is going to be a shade of gray, so that we call as a grayscale image. Now from RGB, we are talking about a different model here, a mixture of C, M, and Y, which is cyan, magenta, and yellow. So how do we obtain cyan? Cyan is obtained when there is an absence of red, which means that blue takes a high value and green takes a high value, you get cyan. So if you look at the other corners of the cube, we will get a clear idea. So combination of blue and red will give you magenta, which means that magenta is the absence of green, and you will get yellow when there is a mixture of red and green, which means that yellow is the absence of blue as well. So that combination of color is also shown on the cube on the right side. So here possibly we can get a better understanding. Different combinations of red, green, and blue displayed on a color monitor would give you your fundamental color RGB, and a conversion from that to CMY basically can be done by subtracting 1 minus R, 1 minus G, and 1 minus B, which means that there is no reflection of red, There is no reflection of green and no reflection of blue to get the colors cyan, magenta, and yellow. So generally the CMY model. So why the need for different models? That is an important question that we must understand. So generally CMY model is preferred for color printers and color copying, and sometimes a combination of CMY might not give you a pure black, and for that reason, to compensate for that, we have a CMYK model where K represents black. So that is, and because black is more predominantly used in printers, generally a CMYK model will be followed. Next is a HSI color model. Uh, we HSI represents hue, saturation, and brightness or intensity. So HSI model, the reason why HSI model exists is because when we as human describe colors, we do not talk about combinations of primitive colors or a percentage of mixture of two different colors. We talk about colors in terms of how bright they are, what is its saturation, and what is its hue. So when you talk about hue, what does that word represent? Maybe in case we are not familiar with the word, we will definitely be familiar with how we describe a particular color. So if you talk about hue, it generally describes how pure that color is. So we say we know it is some shade of yellow, and then we put it on a scale. So that is how we generally describe colors. So we say it is a yellowish shade, we say it is a pure yellow, or it is a light yellow or some shade of yellow. So that giving that kind of a definition is called as hue. Saturation gives a measure of degree to which a pure color is diluted by white light. So when you say something is saturated, a very dark red uh, would generally be described as a very has something is something that has a very high saturation. And so brightness is also another parameter that we say when we talk about a particular color, we say that, or a particular image, we say that it is bright. And so bright is generally a very subjective parameter. um, the other word that we use is also called as intensity. So that is why we call it as a hue, saturation, intensity color model, HSI model. So looking at this particular cube, you can see that one axis, one axis of this particular HSI contains white to black. So which means that we have this range of intensity values from a darker shade to a lighter shade, and the other corner of uh, uh, corner of that representation can be at any corner of that cube. So if looking at that particular color image on the right, we see that we have the color cyan, and it varies across the different ranges of intensity between black and white. So this is how we represent a HSI model. So that can be represented in different shapes. So different shapes will simply mean that along with the grayscale, we are associating with it to a particular shade of color. All right. So these are certain fundamental color models. So let's see how this is represented in MATLAB as well. Maybe I'll basically describe the code first before I get into the software. So let's look at a MATLAB implementation of a color model. So the first thing that we do, we read in an image, we convert it to IM. We use the function IM to double. So we convert it to double, and we save it in the variable name IMG. So the first thing that we're doing here, we're converting an RGB image to a HSI image. So here we use the function RGB to HSV, and we input img, and that output is saved as img underscore HSI. So there is an inbuilt function which performs this action, and so this is quite straightforward, converting RGB to HSI. This can be displayed, right? So I'm not the lines of code that represents how to plot the particular image will be demonstrated on MATLAB. This, for understanding the code, I've simplified it here. And so here we see C, M and Y. So you see how it is concatenated. So when we use the keyword concatenate, we first have to mention the number of dimensions, or how many values are we going to concatenate. So from the image variable, we take every row and every column of the first color, which is red, and every row and column value of the second color blue, and the third color green is multiplied with the value 1, which means that you will get a cyan channel. So cyan channel is going to have a complete combination of blue and green. So that will match with the model that we had learned slightly earlier. When you talk about cyan, it's about blue and green. Right? So we got a cyan channel. Similarly, with magenta, we mix. So again, we are using the cat function. We mentioned the dimensionality, and this is a mixture of red and green. So similarly with yellow, it's a combination of red and blue, right? So that will give a complete yellow channel of a CMY image. Right? So you will be able to see that entire particular color and its representation. So this is a 3-channel CMY, and then we have a 1-channel CMY. So in a 1-channel CMY, what we do here is to get cyan, we simply subtract 1 from red. So this is what we have seen in the earlier theory, 1 minus R. Right? So why do I say this is R? Because the first 2 columns represents the entire rows and columns of the first layer, which is the color red. So similarly with blue and green. So 1 minus blue and 1 minus green is going to give you magenta and yellow. And your final CMY is going to be a concatenation of C, M and Y. So it has 3 values. So that is what we have represented here. So this is what you will be seeing in the code as well. So what we have included here is just so that we can display different outputs that we have got. So you can see that the exact same code is used here, but I'm going to use the figure, subplot, give it a particular title, and represent it so that we can visually see the outputs as well. So that is what are the additional lines of codes that you will see over here. So let's try to execute this code and see what happens. Right. So this is the original image. So this is an RGB image converted to a HSI image. The second is the original image. We have a cyan shaded channel, a magenta shaded channel, and a yellow shaded channel. And third, we have the original image. This is how much amount of cyan is the intensity value. So cyan, magenta and yellow. So what is the intensity of those values, and once we concatenate it, we are getting it in a CMY model color. So I hope this is clear. You can try to run this code yourself and check out the output. Right. Thank you.